Understanding the rate of expansion of the cosmos is one of the great enigmas of theoretical physics and contemporary cosmology. Since the revolutionary discoveries of 1998, the scientific community has been certain that the universe not only continues to grow, but does so at an increasingly accelerated pace. To justify this counterintuitive phenomenon, scientists coined the term dark energy, a still provisional name to describe an invisible and mysterious force that acts as a gravitational repulsion engine. However, even with the technological advances of recent decades, an uncomfortable question persists in the corridors of major astronomical observatories. What is the exact value of the speed at which our universe is stretching? The core of this mystery is known in academia as the Hubble tension, a cosmological debate generated by the glaring divergence between the different methods used to measure the cosmic expansion constant. On one hand, astronomers observe the local and contemporary universe, using the luminosity of type Ia supernovae as true cosmic rulers to calculate distances and velocities, arriving at a specific numerical value. On the other hand, theoretical physicists analyze the remnants of the primordial and distant universe, using the Standard Model of cosmology and the cosmic microwave background radiation, and arrive at a significantly lower result. This mathematical disagreement suggests that either there is a flaw in our current measurements, or there is something fundamental in the physics of the universe that we have not yet been able to understand. Faced with this impasse, researchers from the University of Illinois at Urbana-Champaign and the University of Chicago have brought to light an innovative approach that promises to act as the ultimate judge in this dispute: the use of gravitational waves. Instead of relying exclusively on light or radiation emitted by stars and galaxies, the team led by Nicholas Yunes proposes that the subtle ripples in the very fabric of space-time can function as a third measurement method, completely independent and free from the observational biases of previous models. By cross-referencing this new information with existing data, it is expected that the mathematical precision of the Hubble constant will increase dramatically. To understand the magnitude of this proposal, it is necessary to revisit the year 1915, when the German physicist Albert Einstein presented the theory of general relativity to the world. Einstein postulated that gravity is not an invisible force pulling objects, but rather the result of the curvature of space-time caused by the mass of celestial bodies. He predicted that when incredibly dense and massive objects accelerate, they generate ripples in this cosmic fabric that travel at the speed of light. This audacious theory was only proven a century later, in 2015, when the American observatory LIGO detected the first signal of these waves, originating from the violent merger of two black holes that occurred more than 1 billion light-years from Earth. From this first historic detection, a global network of observatories was formed, including Virgo in Italy and Kagra in Japan, inaugurating the era of gravitational wave astronomy. These gigantic interferometers have frequently recorded the titanic collision between pairs of black holes, neutron-star collisions, and even mixed mergers. Although the idea of using these waves to measure the Hubble constant is not entirely new, the major barrier has always been the lack of precision of the instruments. Unlike optical observations, mapping the exact origin and recession velocity of an invisible event in the cosmos is a formidable challenge, requiring new data interpretation techniques. Accurately calculating the expansion rate requires not only knowing the distance at which a gravitational wave-generating event occurred, but also determining the speed at which that region of space is moving away from us. To overcome this technical difficulty, modern astronomy uses the so-called multi-messenger approach. This strategy consists of capturing the gravitational waves from a collision and simultaneously searching for the light, electromagnetic radiation, emitted by the same event or by the host galaxy. The degree of stretching of this light, a phenomenon known as redshift, reveals the escape velocity. By combining the gravitational sound and the light image, a robust and unbiased measurement of the Hubble constant is obtained. It is precisely within this scope of improvement that the revolutionary technique described in the new study comes in, the stochastic siren method. Instead of sifting through data in search of large, isolated, and clear collisions, which are rare and difficult to cross-reference with perfect light signals, the team proposed focusing on the background sound of the universe itself. This cosmic hum, or stochastic background, is formed by the overlapping echoes of thousands of collisions of very distant and ancient black holes, which cannot be individually distinguished, but together create a continuous gravitational symphony that can be statistically measured. The brilliance of this logic lies in the direct relationship between the density of collisions and the size of the universe. Scientists explain that if the Hubble constant has a lower value, slower expansion, the universe would have a smaller spatial volume than we imagine. In a more compressed space, the same number of celestial collisions would be closer together, resulting in a much more intense and noisy stochastic background noise. On the other hand, if the constant is higher, the space will be larger, diluting this noise. By measuring the volume of this imperceptible hum, scientists can deduce, by exclusion and geometric density, the true size and rate of expansion of the universe. Although the current LIGO, Virgo, and CAGRA consortium still needs to refine its technical sensitivity to hear this stochastic background with crystal clarity, preliminary tests based on existing data have revealed fascinating surprises. This proof of concept, published in the prestigious journal Physical Review Letters, indicated a slight mathematical inclination toward a more accelerated expansion rate. Expectations are extremely optimistic. With the technological advancements planned for the next 6 years, the global network of detectors will become a huge cosmic ear capable of listening to the very breath of the universe, promising to deliver a definitive answer to end, once and for all, the Hubble tension dilemma.